Hello, everyone. I'm Susan Nash, AAPG, and it's my pleasure to welcome you to our second day of our GEODE Project InnerSpace AAPG presentations of geothermal. And the focus of these 2 days has been subsurface characterization. And this is part of a larger Department of Energy sponsored project called GEODE. And we have today 4 presenters, and I'd like to kick it off though with our fearless leader, Higinia Torregrosa, who will tell us a little bit about GEODE. So welcome, Higinia.
Hi, hello everyone. First of all, I want to say thank you to everyone for attending this meeting and this workshop that we created with a lot of care. And as Susan said, this is part of the GEODE dissemination events. And what we wanted to do with this series of workshops was practical workshops for subsurface characterization applied to geothermal. And we wanted to create a very practical workshops where people can take away some new knowledge that can apply in the day-by-day work. And also is focused on people that wants to use or transfer their knowledge from oil and gas into geothermal and see what it's already known in their background and how many things can be applied and learned in this new very exciting world that is the geothermal energy. Thank you very much. And we are quite happy with the numbers of yesterday. We have more than 350 attendees, and hopefully today we will have the same numbers.
Absolutely. And Higinia, I have some great news. Jerry Jeffries was looking at the stats, and we have more than 460 individual people who attended yesterday, but it was like 360 simultaneous at the most at the same time. Wow. Isn't that amazing? Anyway, so thank you, everyone, and thank you, Higinia. And I want to offer a huge thank you to Jon McKenna and MicroSeismic. And Jon has been doing a lot of work in geothermal, but also in microseismic for fracture monitoring, fracture detection, mapping, using passive seismic. And this is a perfect example of technological crossover. So I'll let Jon go into more detail, and welcome.
Thank you, Susan. Yeah, my name's Jon McKenna. Just a quick introduction. I work with MicroSeismic Inc. I've been an employee for 14 years. I do a lot of development for the company as well as the analysis. I am not a geophysicist. I'm a geological engineer, and I'll be talking today about the analysis part of what we can do with microseismic data. So I won't be talking about the processing or anything like that. And I have an undergraduate degree from the University of Georgia in geology and a master's degree in geophysics and a Ph.D. From the Colorado School of Mines in geological engineering. So I hope that I can cross all the boundaries and bring, geologists, geophysicists, and engineers all together. If you look at the top, we have these different banners. These are our different offerings for MicroSeismic Inc. We're active in the oil and gas industry. That's our FracRx offering. And then the second one, CO2 Secure. This is CO2 sequestration that we monitor. And then Karst Alert, monitoring sinkholes. And then Microthermal Energy is our geothermal offering, which today I'll be talking about both our FracRx, which is our oil and gas offering, as well as the microthermal, since they're very similar processes that we can gain information from both of our results that we've and our experience in those fields. So today I'm going to be talking about acquisition methods of how we acquire our microseismic data. We'll be talking about the focal mechanisms, which describe how the rock is breaking and tells us the strike and dip of the fractures that are failing underneath the subsurface, within the subsurface. And then we use those focal mechanisms to create a calibrated discrete fracture network model And since that fracture network is calibrated with the injected slurry volumes minus what's leaking off into the formation, we have this detailed view of the fractures and a calibrated model. We can then inject the actual proppant that the operators are injecting into these systems and track where that proppant's going. I'm going to be talking about different fracture-driven interactions and how the changing in the stress within the rock drives these fractures, how they move around from the development of this dynamic stress that's evolving in the system. And talking about what that is in terms of stress shadows and how we use this to create an integrated dynamic fracture model. And then at the end, I will have a geothermal example. So the acquisition methods, we can monitor from downhole. So we can put our tools downhole, but we don't really offer that anymore because we feel that the surface acquisition is the superior method from our point of view, that we get the best results from monitoring from the surface. So what that means is we put geophones right at the surface, and we have these two different surface arrangements, a surface frac star and a near surface buried array. Now our frac star, we have a lot more geophones than the buried array because the frac star is laid out right at the surface where we have more cultural noise. And when we rely on the vast number of geophones and the power of the stack. So when we stack all this information, we have these little squiggles of data coming in that the geophones are collecting. And if we stack all the data, then the noise is canceled out and the signal is enhanced. So a surface array is a temporary array. It can be laid out and deployed very quickly and picked up very quickly. It's also flexible. We can wrap it around. For example, if different property owners don't give us permission, we can wrap around their property very easily or avoid different cultural noise. And then the near surface buried array, we have a lot less geophones, but the reason being is because these geophones are placed in a drilled borehole. So we drill a shallow borehole and place the geophones about 300 feet depth. And we put the geophones at a shallow depth, but just deep enough where we've really minimized that cultural noise. And then we also offer a DAS interrogator. This is distributed acoustic sensor monitoring, where we are using fiber optic cable to act as our seismic array. And like I said, I'm going to be talking about our focal mechanisms. When the rock breaks at the subsurface, we get this P-wave radiation pattern that's detected at the surface of our geophones. And when what we see is part of the array will experience a positive or a first motion going up, whereas part of the array will experience a first motion going down. And that translates into how that rock is breaking. So this is showing kind of that positive first motion going up versus down. And that is dependent on how that rock is actually breaking. Where it's going up, that is would be your tension, and where it's going down, that's your compression. And that translates into, for example, the strike slip mechanism, where we see 4 lobes of the focal sphere. And you can always figure out what that means by these pictures. This is a lower hemisphere description of the stress from these fractures. The white is where you have your compression, and the black is where you have your tension. This red line is showing where your active nodal plane is. There is also an auxiliary nodal plane that is an equal likely solution, but I'll talk about how we figure out which fracture plane is failing. So in this example, the strike of the fracture would be oriented in this red line at an azimuth at about 120 degrees. you can, because the compression axis is the white and the black is the tension, the movement is would be strike slip on a vertical fracture. So since we're looking straight down on it, it's a vertical fracture. And the movement goes from white to black. So it moves to the dark side. So this would be a left lateral displacement. So you're looking across the fault, and as you look across, the movement would be to the left. So that would be a left lateral. And so that's a strike slip. It's depicted here. And I talk about that rake, where the rake is in the direction of the strike, as opposed to this top one, which is a dip slip mechanism, where the slip is in the direction of the dip, so going down, as opposed to strike slip, which is moving horizontally. And so this dip slip mechanism, you'd have a negative here and a positive in the white. So the negative would be moving down relative to, which would be the hanging wall, relative to this black, which is the foot wall. And so here's an example of what that looks like. The rock is breaking at the event. That signal is propagating up to the geophones at the surface. Some of the geophones are experiencing first motion down, some first motion going up, and that's how we determine that focal sphere. And so here's those different focal mechanisms placed on the hypocenters of the events. We're looking in map view. We see really two dominant focal mechanisms for this example, and these are two horizontals. The black are the wells themselves, and so when we look that there are two dominant focal mechanisms, this strike slip mechanism and this dip slip mechanism, and like I said, the active nodal plane is going to be the actual nodal plane where the failure is occurring, and that will line up with our event trend. So you can see this is a fault that was reactivated during the stimulation of this western well, and so this is moving as a strike slip, a left lateral strike slip with a strike of about 120 degrees, and it is a vertical fracture. As opposed to these dip slip mechanisms, these are going to be, the fractures are going to be slipping in the direction of the dip. This strike is going to have an azimuth of about 70 degrees, and again, the active nodal plane is determined as the plane that is parallel to the trend of these events. And so here's a clear example of an array and the P-wave radiation pattern. So we're looking down in map view at a single event, and we see the events with all the different polarities, red and blue, shown. And you can see that it really translates very nicely when we use a pure double couple solution with this strike slip mechanism. And you can see this, all four quadrants of the focal sphere illuminated, and the higher amplitude in the middle of the focal sphere that's decaying as you get to the nodal planes. And so if we can assume different solutions, I'm showing on the left just a pure double couple solution, where on the right is assuming a full moment solution. A pure double couple solution means that we assume no volumetric occurrence of the fracture, just pure double couple, or just slippage along the failure planes. And so that's what the focal mechanism would look like. But when you look at this blue portion, you see that the blue is coming together, whereas the red is separated by this blue portion. Whereas, so if we assume a full moment solution, which incorporates the volumetric component, that shows that there is an opening portion, or like an explosive portion of this focal mechanism. So this is demonstrating that this is not only slipping along a strike and dip, but it's also actually opening of the fracture. And that can become really important in understanding how much those fractures are actually dilating or contracting. So a little bit more about how we get an idea of how the rock is breaking in the formation. We can create we can track events as they occur in time and space. So as they're occurring in time and space and propagating along their individual fracture planes or along these different faults, we can track the orientation of those planes by tracking the events occurring in time and space and plotting planes that fit those events as they occur in time and space, and then plot those 3D planes on the stereo net. And then we can compare those also to our active nodal plane. So if I back up to this one, it would be like tracking all these different dip slip events with this kind of 70-degree orientation. And so we're plotting the 3D lineaments, or those planes that fit the events as they propagate in time and space, and then comparing them to our active nodal plane to make sure that we've picked the correct active nodal plane. If we have not picked the correct active nodal plane, like I said, there is a secondary auxiliary plane, then that would be, we would switch to that other nodal plane. So we want to make sure that we pick the correct nodal plane and it matches our 3D lineaments. That way we can move forward and create our DFN and do our stress analysis and do our analysis correctly the first time. And it's important to note that those 3D lineaments can be very complex based on the different fractures that we're observing. So you can see all the different orientations of the fractures that are occurring, which are present on all these 3D lineaments. And it's also then when we look at our active nodal plane, these two pictures are gonna need to match up so that we know that we've picked the correct nodal plane. So you can see all these different planes that are being activated that are matching up between the 3D lineaments and our active nodal plane so that we can create a very accurate DFN model. And so this is showing an example of 7 different wells that were treated in the Williston Basin, and how we create our fracture network to be very accurate to reflect all the different focal mechanisms that we're seeing. And what I want to kind of back up and say, what is going on when we're detecting this seismicity down in the formation? Well, way back in 1976, Art McGar, I think he's a famous USGS scientist. I actually worked for the USGS from 2001 to 2011. This was taken from the Rocky Mountain Arsenal near Denver, which is actually where I worked in the Denver or Golden, Colorado office. But this is showing the seismicity that occurred near the Rocky Mountain Arsenal as they were injecting all this volume into the ground. So they're having these disposal wells, they're injecting this massive amount of volume into the ground. And then this shows the seismicity that was detected during this injection. And what you can see is that there's really 3, if not 4 main episodes of when they're injecting, and we're seeing those same episodes, populations being detected in the seismicity, indicating that Art McGar discovered that the volume changes of the rock. So as you inject fluid into the ground, you're actually creating these fractures that are opening and creating fractures that are opening and creating an increase in volume of the fractures, and that volume is correlated with the seismicity that's detected. And then there's even another population of events after they stop pumping, maybe showing that these fractures are now closing on themselves. And then that seismicity is really decaying down to zero as those fractures are then all closing on themselves. And so he related that change in volume to that should be, so that change in volume, that delta V, should be correlated to the total seismic moment, or that's another way to express all the different magnitudes of the events. So that the larger the magnitude, the larger the seismic moment, that volume change is directly correlated to the seismic moment that we're detecting, as well as to the shear modulus, or the rock rigidity. That's the rock property of the rock, as well as this K factor. And this K factor is kind of a scalar that it says that has to be applied. It's a factor. If you compare directly the volume that's injected to the volume that's being translated from the seismic moment, we say, okay, that seismic moment, if you take the seismic moment and the shear modulus, we can actually back out the volume, actual volume change that's occurring, that's modeled from the measured seismicity. So we're saying, what's the volume we get from that we are modeling from the detected seismicity versus what's the volume that's actually injected. And there's this K value that's used as a scalar that says we don't have a perfect match. And the reason that we don't have a perfect match, our modeled volume is always smaller than the actual injected volume, because we don't detect every single seismic event. Some of the events are below our detection threshold. So we have to realize that we don't detect every single event, so we have to account for that missing population. So I have adapted that same methodology for creating our fracture network, and we create our DFN. So all our fractures are centered on the hypocenters of the events that we detect. The fractures are oriented by the focal mechanism in terms of their strike and dip. And then the area of the fracture, we should use this equation. The seismic moment is equal to the area of the slip plane times the shear modulus times the displacement along that fault. And we detect from our array the seismic moment of each event as well. And then we know the shear modulus based on a well log drilled down into the formation. So we know the depth of the event, and we know what the shear modulus is at that depth, so we can make a good estimate on what the shear modulus is at that hypocenter, and we measure the displacement of the event, so we can actually measure the area of each of these different fracture planes. So now we have a good estimate on how we have a good measurement on the fractures, how they're oriented and where they're located. We know which ones are bigger, which ones are smaller, and where they're distributed through the formation. And so then we want to calibrate that, let me also back up. We also then need to know how much those fractures are opening based on the aperture of the fracture. This is how much the fracture is opening. And we use a correlation based on outcrops in the rock. So we're looking at actual outcrops, and there's a nice correlation that says the longer the fractures, the greater the fractures are going to be dilating, or the greater that they're going to be opening. So we initially make an estimate on that, how much that fracture is opening based on the length of the fracture. And then we further refine that opening of the fracture based on our focal mechanism measurements, that we can actually get the volumetric percentage of each of these fractures. And so what this curve is showing is that our normal dip slip mechanisms have the greatest amount of volumetric fracture openings. So the ones that are slipping in the direction of the dip slips, or the normal mechanisms, are actually opening more than the strike slips. The strike slips tend to just slip in the direction of the strike, but don't really dilate nearly as much. And so this becomes important. So this is primarily from a normal stress regime. And we'll be talking about what that means further in the presentation. So now we have that DFN, and we want to calibrate our DFN and say that the way that we calibrate is we compare our injected or our fracture volume to the injected slurry volume minus what's leaking off into the formation, and say that our final fracture volume needs to be equal to that total injected volume minus what's leaking off into the formation. And so the leak off is not effectively creating fracture volume. And so that's why we need to know what's being injected, what's actually leaking off and not creating fractures. And now we know that that's kind of the volume that we're expecting to be created and to be modeled by this total DFN. And like I said, the reason that we do that is we don't detect every single microseismic event. Some of those events are below our detection threshold, so we have to account for that. And so what we do is we scale up these fractures. They kind of grow a bit in the direction of the strike and dip to account for that missing population that we didn't detect. And so now I'm going to get into fracture-driven interactions. This microseismic monitoring permits evaluating interaction, for example, with parent wells and child wells. So a parent well is a well that's been drilled and produced from, and then they drill child wells. So this is taken from oil and gas. And when you drill a child well, if there's a pressure sink, a lot of that energy will go back towards that depleted well. So this is kind of showing what happens with a frac hit. A frac hit is common in unconventional horizontal development. And so the production, so if you drill a well, this is looking in depth view, drill a well, and then you deplete you're removing hydrocarbons and water from that area. You're creating a pressure sink or an area of low pore pressure. And then you drill, and later on you drill an offset child well. If you inject a high pressure stimulation to hydraulically stimulate that second well, if you don't take any precaution and pressure up the parent well, then all your fluid is going to go back into that pressure sink of the parent well. And that production from the parent well creates a zone of low pore pressure and changes in geomechanical properties. And later on, when you inject to stimulate your child well, that child well can grow towards the parent well and lose a lot of the stimulation. So you're not effectively creating fractures around that child well, and you're just injecting and losing a lot of fluid into the parent well. And so the reason I'm talking about this is because in geothermal wells, a lot of times we have these doublets where we're drilling an injection well and a producing well. And a lot of times they treat for enhanced geothermal systems, they drill the injection well, they inject and hydraulically fracture that injection well, and then they look at the microseismicity associated with that injection well and see that stimulated rock volume around that injection well, and then figure out where they want to drill their second well, their producing well, and then they'll hydraulically stimulate that one at a later time. Well, if you stimulate the lower injection well and then allow that pore pressure to bleed off and dissipate and go away, and then drill your treatment well and inject into that one, if you don't take any precaution to repressurize the first well that's been treated, then a lot of your injection energy is just going to go back to the parent well and not effectively create fractures around the second well. And since creating fractures is directly correlated with creating fracture area and enhancing permeability, then you're not effectively creating permeability around that second well being stimulated. And that preferential growth can create a compromised stimulated rock volume of the child well and affect the production on that parent well. And so let's look and see what an example would be from microseismicity. So we have a parent well here, vertical parent well, and then we have two child wells that are drilling. So this parent well was drilled and then depleted from, and then they drill these child wells and they're injecting fluid in these perf clusters. SH max has an orientation about 80 degrees. And you see that this first stage that's stimulated, the stage is not affected by the nearby parent well. We have good symmetry of the events around the child well that's being stimulated. The events are propagating in the direction subparallel to SH max, and there is some interaction with that child well B. And then as we get closer to the parent well, because there's a depleted area around that parent well, now all that microseismicity is going back to the parent well in the direction of SH max, and we can start to delineate that that extent of the depletion around that parent well. And at the same time, we see a slight increase in pressure in that parent well. Now, as you get closer to the parent well and in line with SH max, now we see that this stage has hit the vertical parent well, and we have a large increase in pressure also observed on that parent well, and subsequent stages are going back to that parent well. And we see a lot of energy going into that parent well. And like I said, our mechanisms tend to change as you're also injecting. We see these events also occurring on the child well. So, but what's important is that the mechanisms are changing. They're going from, these are all dip slip mechanisms where you're actually opening up the fractures. And then in this case, they're stimulating child well here, and then stimulating child well B, and then child well A, then child well B, then child well A, and then so on. And as you do that, this is just showing the microseismicity occurring during the stimulation of child well A. We get a stress shadow effect around the previously stimulated area, and we will see subsequent events occurring in the area that's also already been pressured up, and the mechanisms will change in the area that's already pressured up and changes from dip slip to strike slip, and we can see exactly where that stress shadow effect is occurring, and I will have some examples of what that looks like. And so then, because we have a fully calibrated DFN for our fractures, we can inject proppant into that formation to track and fill out through that fracture network with the proppant. So we're filling out the fractures with proppant, injecting into each different stage through the perforations that where the injection is occurring, and the proppant is building out through that DFN until all the proppant volume is used up, is filled up into those fractures. And the way that we fill those fractures is based on the measurements of where you're creating the fracture volume. So for example, if you have one stage that's created and you create a lot of fracture volume that goes shallow into the formation, then our fracture model will be tracking where that fracture volume is being created by the microseismicity associated with that particular stage, and building out through that DFN based on where you're producing your fracture volume. And so if you build it up shallow into the formation, now you create a stress shadow around that shallow part of the formation, and your next stage will respond to that increased stress in the shallow part of the formation. Your next stage may now build out, will now frac deeper into the formation in response to that stress shadow on the previous stage that was shallow. And so our proppant model will now build out deeper down into the formation, because we're making measurements showing where we're building out the fracture volume for each stage. So here's an example of our workflow. We take all the microseismicity taken from each well that's being treated. We create a calibrated DFN fracture model for all the different fractures centered on those events. And then we inject the proppant into each stage based on where you're building the fracture volume. So some of them are preferentially growing to the east, whereas some are preferentially growing to the west. And if we look in depth view, some are growing preferentially shallow, and some are preferentially growing deeper based on the microseismicity that we're detecting in real time as those fractures are growing. And then we can place a geocellular volume around these fractures, and every cell that contains a fracture is retained in the model so that we can then calculate a stimulated rock volume associated with these injections. And we place a cell. These are in this case 50 by 50 foot cells, and that's sized appropriately to mimic your drainage pattern around these different fractures. So you'll be draining not only within the fractures, but about a 50 by 50 foot cell around each of the different fractures. And so we can get an idea of that total stimulated rock volume. And the colors are showing our enhanced permeability. And the way that we get that is each of these cells, we're looking at how the fracture intensity within the cell and the apertures of each of these fractures, how much those fractures are opening. So we're looking at the enhanced created new fracture volume or open void volume within each cell, and we can then determine how much increased void volume is in each cell, which can then be related to enhanced permeability, and we can make those measurements in the X, Y, and Z directions, which can then go into a reservoir simulation to simulate, for example, fluid flow through this new enhanced permeability system. So now I want to shift gears and talk about treatment order effects. So like I said, if you have two wells, like if we're looking in depth view, an injector well and then a producing well, if you drill well one, your injector well, and then this is like an enhanced geothermal system, you're hydraulically stimulating, hydraulically creating fractures within that lower well, you're going from toe to heel. So you start injecting on stage one at the toe, and then stage two would be further heelward from stage one, and so on. You're going from toe to heel with your stimulation. Typically, we see compounding pore pressures occurring from stage to stage. So you're getting a compounding effect of the pore pressures as you go from stage to stage. So we tend to see lower microseismicity or smaller fractures being created at the toe, and getting more compounding pore pressures as you get to the heel, creating larger fractures towards the heel. And a lot of times, you have lower pore pressure in the shallower part of formation, so you get fractures that are growing upwards and growing towards that producing well. And like I said, we could see where those fractures are occurring and where we need to drill that second producing well based on our half lengths and where we're getting the microseismicity. And then if you drill that second well, if you inject rapidly in time right after the injection of well one, then those pore pressures will be retained, and that fracture volume will grow away from the first portion of the stimulation. So these fractures are growing up, and they're pushing the stimulation from the second well away from where we have these high pore pressures being created from the first well. And what we see when we model those fractures and look at that fracture volume, that you get higher fracture volume due to the compounding pore pressures from toe to heel, as well as from the stimulation from well 1 to well 2. So greater amount of fracture volume from toe to heel, and from the first well being treated to the second well being treated, as long as they're stimulated within a rapid time interval, that you can take advantage of the pore pressure created from well 1 and not allow that pore pressure to completely go away. And the areas where we have overlapping fractures, we have compounding pore pressures, and the stresses will actually rotate slightly. And our focal mechanisms within that area of overlap will be changing from dip slip to strike slip in a normal stress regime. So we will be able to identify where those changes are occurring. And so in map view, if you look, stimulate well 1 followed by well 2. Well 1 is your leading well, well 2 is your trailing well, and blue is your SH max. It would be oriented east-west in terms of your background SH max, but during the injection, if you lead with well 1 in map view and followed by well 2, there would be a rotation expected during the stimulation of well 2 in between the two wells. Whereas if you and then so where we if we look at the rake changes, we see that where we have that overlap, our colors are changing from blue to red, indicating your stresses are changing from your virgin reservoir stress to this altered stress in red, indicating that you have some stress rotations, compounding pore pressures, and there's some stress shadow effects in that area. Consequently, if you were to change, if you were to change the order, and you had this well leading well 2, we would have a rotation in the parent SH max, which if you have faults oriented in that direction, you could preferentially cause faulting to occur due to that rotation in the stress. So why do we have stress changes? It's because, so we have rotations in the stress, but we also have changes in the magnitude of the stress. And this shows that here's the center of your fracture, and this is distance horizontally from the fracture. You have an increase in stress that's greater in your minimum horizontal stress than it is in the maximum horizontal stress, and greater than it is in the vertical stress. So you end up with also rearranging the relative magnitude of the stresses. And so your virgin reservoir stress in terms of sigma 1, 2, and 3, you would be increasing sigma 3 and also increasing sigma 2, but less so, and less than sigma 1. So you're effectively changing your phi, which is saying, so phi is saying for this one, it would be a 50% horizontal stress ratio versus this one, it's very low, about 0.05. That sigma 3 is getting closer to sigma 2 because you have this increase in sigma 3 that's greater than sigma 2. So these are all happening in the reservoir, and we can measure all these changes. And so to illustrate some of these effects, I want to show, I want to stack all the microseismicity on top of one another, or kind of reference them all to your injection stage. So each of these stage centers, and then we can create these heat maps to get an idea of what a single stage would look like. And so that's what I've done here. I've stacked all the stages on top of one another. We're looking in map view, well 1, well 10, and well 9. And we're just looking at these colors where it's your changes in stress are changing from your virgin reservoir stress state to an altered stress state. And what I'm suggesting is that your stress shadow impact on neighboring wells is time dependent on your stage lag time. So how long it takes to go from one stage on one well to your opposing stage on your neighboring well. And you can, so when you have no other wells treated in the area, there's no other stress shadowing effects. All your fluid, which is shown here as your blue colors, and your modeled proppant shown as your contours, is right around your stage center being treated and really staying close to your well. And so you're stimulating right around your well being treated, as opposed to this second example. We have an offset well over here and an offset well over here. This is like a triple zipper. You treat a well here and then an offset well here. And then within 0.2 days, you treat the center well. We see the effects, these stress shadow effects on these offset wells. And we can take advantage of these stress shadow effects. And our new injection will be sandwiched in between these stress shadow effects that are created on these offset wells, and our fluid and our proppant is retained in between these two stress shadow effects. Versus this final example, this is a depth view showing what happens when you treat a shallow well and then wait 18 days later and go in and treat your deep well. Well, now there was a stress shadow effect that was created around the shallow well, but now it's dissipated and gone away. Whereas when you inject into the deeper well, all your fluid and proppant is going to be going back to that shallow well because there is no pressure shadow around that shallow well. So this is what I was talking about with if you stimulate a deep well first and then wait months or longer before you then go in and stimulate your shallow well, you may not be effectively creating fractures. You just be sending a lot of your fluid and proppant back to the previously treated well. So let's look at this example more in depth. We can also do an inversion of the focal mechanisms, which gives our estimate of our determination of SH max, which in this case is oriented at about an 80 degrees, whereas the microseismicity occurring on this left well. So there's a well over here that's being injected and then injected on a well over here. And then after 0.2 days, they treat the center well, and the red is showing the stress shadow effects on either side of the wellbore. And we see an apparent rotation in SH max as you go off to the left. Off to the left, there's an apparent left lateral rotation in SH max, and off to the right, an apparent right lateral rotation in SH max, which matches theoretical geomechanics. And this shows where those offset wells are located. And this shows our inversion of our virgin reservoir stress state and our apparent left lateral rotation on the left and apparent right lateral rotation on the right. And this shows where those events are located. So the virgin reservoir events are located right around the wellbore, these blue events, whereas the left lateral rotation are primarily on the left side of the wellbore, and our right lateral rotation are primarily off to the right side of the wellbore. And then, so these cool colors indicate virgin reservoir stress states. They're dominated by dip slip mechanisms. They're represented by initial fluid propagation into unpressured rock. You have greater dilation tendency. The fractures are opening, the apertures are opening. Whereas when you have altered stress states, they're dominated by these strike slip mechanisms, or these red colors. And this represents reactivation of previously pressured up rock, where pore pressures are compounding, and you have decreased dilation tendency, so the fractures are not opening nearly as much, and it responds to resistance in slurry volume. So as you're injecting, you have these high pressures, your fluid will not be going over here nearly as much as staying in the virgin reservoir stress state. And so we know that the dip slip mechanisms, the cool colors, are creating the greater amount of fracture volume, and the strike slips are creating the lower amount of fracture volume. So we can create these fracture volumes where the virgin reservoirs have higher fracture volume that's decaying to lower fracture volume in the areas of where we're getting strike slips. And then we can create our total fracture volume. So even though we're getting all these microseismic events, all microseismic events are not created equal. And what it translates into is you're creating most of your fracture volume in the area of where you're getting those dip slip mechanisms, and very little fracture volume in the strike slip mechanisms. And so we can then inject the proppant into that fracture volume until we've used up all that fracture volume, and it's guided by where you're building all that fracture volume, so it forms the core of this this entire fracture volume, and then we can get an idea of where all that proppant is going. And we're looking at this kind of targeted interval based on which is represented by your average well spacing and your average stage spacing to get an idea of, you know, is the well spacing appropriate and is your stage spacing appropriate? So again, you know, to reiterate, if you initially treat your lower well followed by your shallow well, you create fractures. But if you allow all those the pore pressure within that lower well to dissipate, and then you go in and stimulate your upper well, in the areas where your fractures intersect the previously treated well, you'll have a lot of fluid just going back to the previously treated well. Whereas in the areas where you're creating new fractures in between your first well, so if you're creating a fracture here, that one will actually be growing you know, outward as normal and shallow, creating fracture volume right around the second well being treated. But if there's no built up pore pressure, no stress shadow around that second well, fluid and proppant will just be going back towards that previously treated well. So we want to take advantage of these stress shadow effects and stimulate them kind of simultaneously, so we can create the most fracture volume, then maybe let the pore pressures completely dissipate, and then cause breakthrough on both wells to break through and connect all these fractures. So maybe if you initially treat the first well and then go in and treat the second well later, a better way to do that instead of just stimulating the second well would be to repressurize this area and build that pore pressure back up and then stimulate the upper well. So you inject low pore pressure, keeping your pressure below the fracture closure pressure so you don't create new pressures, a low rate, long duration pressurization step to refill that lower well and repressurize it before you stimulate your second well. So here's an example where there's a parent well drilled here. They drilled the parent well and then they depleted from it, and then they depleted it, and then they drilled these offset child wells. And then this is showing where they refractured their parent well by taking advantage of this two-step methodology where they repressurized it and then stimulate it. If they don't repressurize it, they just create fractures that blow out the heel, because we have a high pressure contrast from heel to toe, and you just blow out the heel and not effectively stimulate the toe. Whereas if you repressurize it and then stimulate it, we get microseismicity going from heel all the way down to the toe. And then when you re-inject on your child well, you will contain the fracture. So if you repressurize this parent well and then stimulate this child well, your fractures will be contained on the child well and not be going back to the parent well. Whereas if you drill this parent well and don't repressurize it, when you stimulate the child well, all the microseismicity will be going back to that parent well. And by repressurizing the parent well, you'll save the child well as well. So this is a local type curve showing oil production, and then without re-stimulating the parent well, those child wells will underperform because you don't effectively stimulate the child wells. Whereas if you repressurize that parent well, those parent wells will be better in production because you're not sending all that fluid back to the parent well. So now finally, I want to get into the geothermal example. This shows the geothermal activity associated with injection on this, this well here. And here's the microseismicity that's occurring, the increased fracture volume. And we see this is a fault that's occurring. We see that during the injection of this well, actually, they're injecting in this area. They're injecting here throughout the entire system. This is the pumping station, and then this is where they're producing from. And this shows where all the activity or fluid flow is occurring through the fracture network, primarily along this fault that's also propagating through here. So in this example, we see most of the activity is actually occurring deep and along this fault system. It's occurring right along, here's your producing well. And what occurred was we were only monitoring over from December 1st through December 11th, a short amount of time. We see events occurring when they're pumping, but then when they stop pumping, we see a whole bunch more events occurring. So during the injection portion, these fractures are open and just being held open. But then when they stop pumping, these fractures are closing due to the pore pressures decreasing, and we see even a lot more events occurring during the cessation of the pumping as these fractures are closing. And so this volume is showing our total fracture volume that's being created during the entire stimulation of all the activity. And then we also get some real discrete events that we can get strong focal mechanisms on. So these are real strong events that we get good focal mechanisms that describe that we can get these beach balls that describe how the rock is breaking. And then we can get the stress state associated with those different focal mechanisms that describe, for this example, showing that SH max is primarily north-south in this area, which is in Nevada, north of Reno, where we get SH, you can deduce the actual stress orientation in terms of sigma 1, 2, and 3. So finally, in conclusion, these stress shadows develop around previously treated stages due to elevated pore pressures, then dissipate over time and return to your virgin reservoir stress state. That virgin and altered stress state can be identified by performing a stress inversion of the focal mechanisms. And the regions identified as experiencing altered stress state are also regions experiencing high pore pressure, which restricts slurry propagation from subsequent injections and have low dilation tendency. And after that pressure dissipates through the newly fractured network, new injected high pressure from fluid on offset wells can either overcome the dissipated pressure from the previously treated wells or migrate around it and cause new fractures. And the region identified as experiencing virgin reservoir stress state represent initial fluid propagation into unpressured rock where fractures have highest dilation tendency, and that modeled proppant propagation through the DFN is guided by the increased fracture volume from that virgin stress state. So that's all we have here. If you want to get in contact with me, here's my contact information, as well as Annalise Anderson, who is our sales representative associated with microthermal energy. So that's all I have. Hope you guys enjoyed the presentation, and I'll open it up for any discussion.
Okay, thank you, John. So we're right at the top of the hour. So in theory, we have no time, but let's make 5 minutes of time for.
Sure. Sorry, I kind of went over there.
That's okay. No, it was really, really good. And I mean, I'm so glad we're recording this. And just to remind everyone, you'll get a link to the recording, and we're also going to post it in AAPG in our mirror site. So there are lots and lots of questions. Why don't you take a look at the Q&A, the chat, and see if any of them really jump out.
Let's see. Yeah, so not all fractures result in seismic events. Some of them could be aseismic. So if you have pure dilation and no actual shearing, then theoretically you won't get any, you won't hear the fracture occurring. But typically our microseismicity outlines any of those actual pure dilation events. So we actually still get the footprint around those pure dilated events. Let's see. Yeah, so what's the max? What is the maximum magnitude of the events? You know, when you're reactivating some faults, they can be pretty big when you're injecting. Typically, not much larger than a magnitude 2. That would be kind of on the Richter scale. So still lower than anything that's being felt at the surface. Let's see. Sorry. Let's see. The next one. Yeah, we have a lot of different publications. I have them listed here, but if you contact me, I can make those available. You can search up my name, Jonathan McKenna, and use keyword microseismic or fractures, and you can find some of my publications, or stress shadowing effect, induced seismicity. You know, there can be induced seismicity in geothermal wells for sure, because these are near, volcanoes. They can be within volcanic regions, and near a lot of times in highly fractured rock. There can be different faults that can be reactivated. So what would be the impact of high temperatures in geothermal systems? You know, we would see these geothermal effects. So when you're injecting, we tend to see fractures propagating in one direction. And then when it heats up and gets hot, the fractures can rotate due to these high temperatures. So you have thermal effects causing rotations and stress. And we can see that in our stress inversion. It says surface arrays have higher vertical uncertainty. What is the vertical uncertainty? We are typically in vertical uncertainty right around the 30 to 50 foot range. So it's still pretty small, and it's constant throughout under the array. And yeah, this can be elaborated to different geothermal wells, especially enhanced geothermal systems. And then you can go into where you're getting more enhanced permeability from our geothermal analysis, or our enhanced permeability analysis. The magnitude of the microseismic events tends to be down to about a -2 to a -3. That's about the lowest we can get. And all of this can be integrated so that you can do reservoir simulation. You can do a Moore circle analysis to determine what pore pressure is required to reactivate different fracture sets, and what are the effects of the stress shadow and the time dependency of the stress shadow. So I'm just kind of going through. That looks like
I think we have time for one or two more, and then we need to get ready for the next one.
yes, so it says Taylor Swift concert, the US generated seismic equivalent to a 2.3. So that would be kind of the highest magnitude that we detect generally from kind of like earthquakes or faults that are reactivated. That can be reactivated. It's not as common unless you're in a really highly seismically active area.
So John, is it fair to qualify if any issue people concern about seismicity, we just say Taylor Swift 2.3 and everything we do is below that threshold?
Yeah, the closer you are to any faults is gonna be the prime indicator of if you're gonna reactivate it, as well as the amount of volume that's being injected. So the greater volume, the greater the likelihood of reactivating, or if you can lubricate the fault, or if that fault is already activated versus if it's not if it's dormant. These are all going to be different factors. Yeah, magnitude 2 felt in Oklahoma. Absolutely. These are from injection wells primarily, is what this person's referring to.
That's
Jeremy,
super
thanks.
interesting. Yeah. Well, that's good to know, and thank you again. If you want to, if there's one more that you'd like to address, John, we've got time, and then we'll move on.
Says lots of progression in microseismic since I saw in 2014 with Peter Duncan. Have you monitored wells with Frac RX after 3 months? Or after 3 months or after 6 months of production, and then you treat an offset neighboring wells, we see a lot of activity going back to those depleted wells for sure. So it's dependent on how much volume is depleted, if you're going to send fluid back to it. So like I said, if you treat your one well that one well, and then you wait a long time with that stress shadow goes away, if you treat your next well, you'll be likely losing a lot of pressure and fluid back to that initially treated well. It says, have you tried confirming communication between geothermal wells, production and injection with dyes to ensure the induced fracture is affected? Absolutely. And I've primarily done it with oil and gas wells, and it's actually from this injection well. And I have a publication from it. It's from 2023. We had tracer that was very correlated with the microseismicity. I don't have time to go into it, but yes, we've used dye, and it's very conclusive.
That's great. So why don't you advance to the last slide with your contact information so that we have that in the recording as a little placeholder, and everybody can jot down the information. And really appreciate this. This is great. It's so
yeah. So you could reach out to me. That's my email. That's my phone number. Feel free to contact me. We can continue the discussion, or I can give you a presentation to your organization.
This is great. Well, thank you, John. It's wonderful, and want to just express our appreciation. And we'll move to the next presentation, which is Steve Tedesco. So thank you.
Sounds good. Thank you.